Hello guys, so in these slides we'll go over chapter 5. Consider this as the revision that we couldn't have time for due to the unforeseen circumstances. So the two main points that I'll discuss are basically how to find the magnetic field using Ampere's law and symmetry, and the second point is how to find the magnetic vector potential at large distances using multiple expansion for any localized current distribution. Pretty much similar analysis to what we did in at the end of chapter 3. Okay. Okay, so let's look at the concept of current densities, which we'll need to discuss when we discuss the details of this chapter. So the best way to introduce this concept is to introduce something or review something similar, which is a charge density. So there is a side-by-side comparison, so you can see what are the differences and the similarities between the charge distribution and the current distributions. So let's look with the charge distributions first. So there are different situations where you can have charge distribution. So you can have a continuous charge distribution distributed over one-dimensional line like this, or you can have charges distributed over two-dimensional surface like this, or you can have some charge distributed in 3D like a cloud of charge or something. Okay, and so in the case of continuous charge distribution, what you do in one dimension, what you do is that you divide this whole line into little distances, each of which is called dl. And within every dl, there's some amount of charge, we call it dq. And in general, maybe the charges over this dl is denser than the charges over this dl. So basically, this quantity, which we call the linear charge density, can vary from one point to another in along this line. Okay, and this point is emphasized by choosing two different numbers for lambda at two different locations, just to say that lambda could be different at different locations. So here the charge might be denser than the charge there. And same story with the surface charge distribution, which you can also define if you have a surface. So again, you divide this whole area into little areas, each of which is called dA, and every patch contains an amount of charge dq. Then this quantity is the definition of a surface charge density, which is which is a way to quantify how the charges varies from one point to another over this surface. Similarly, with rho, you can define a volume charge density, which is, again, you divide this whole volume into little volumes, each of which has the amount d tau. And then this quantity is what we call rho. And again, that rho can vary from one point to another in space. Okay, so what if now these charges are moving? So you have here like a stream of charges down this line. They are moving. They are moving with some velocity, say. And same story here. You let somehow the charges move down this surface, and these charges are also moving in 3D. So once you have charges in motion, then we talk about something called the current, and current is nothing but a flow of charges. Okay, so let's consider every one of these cases, and let's see if we can define quantities similar to the charge densities here. All right, so in one-dimensional line, you have a flow of charges, then there's a current I here, and you can make use of this analogy. It's always useful in the situation that you can treat this line as just a lane of some particle, or a lane like a lane of cars in a traffic. So there's charges moving in this line, and there's only one lane with one current. The current here is like the same at every point. By the way, we are discussing here only magnetostatics. So the magnetic fields which is going to be produced by these currents, as we'll discuss later, is time independent. Okay, hence these currents are steady currents; they do not vary with time. So the current at every point is the same. So just one lane with one current, we call it I. And what's the definition of I? This is the amount of a charge crossing a point per second. Okay, so a point here, just pick some point down this line. I denoted this point by this mark, this green mark. So you just sit here, count how many charges are crossing this mark per second or per unit time, and this is your current by definition. Okay. So what if now we are on a two-dimensional surface, and again you have charges which are moving. So again you have currents. So imagine we want to have a similar description to the one that we have here. I don't know why. Yeah. So in the sense that we need to talk about like lanes, and there's a current in every lane. So what we can do about the surface, because now you have an extended object, it's no longer a one-dimensional line, it's a two-dimensional surface. So you can you can have a similar treatment by just dividing this whole area into little lanes, and every lane has a little width. We are going to call it dA perpendicular. So this side, this is going to be called dL perpendicular. Okay, and let me go back to the laser pointer. Okay, so on this surface there are many lanes. Each has some current. We are going to call it dI. So this is the amount of the current here, and this is the amount of the current here. We are going to call it dI, just in the same way that the amount of charge here was called dQ, and the amount of charge here was called also dQ. And just in the same way that dQ can vary from this patch, you can have denser charges here, so the amount dQ here can be different from the amount dQ there. Same story, you can have a different dI on this lane than on this lane. So dI can vary from one lane to another. Okay, so dI again by definition is nothing but a current. So it's the amount of charge crossing what now? You notice that you no longer have a point. So when you define a current, so because this lane has some width now, so the way you're gonna define the current is that the amount of charge crossing a lane per second, and crossing a lane now, the lane has the width. Okay, so that dI is how much current is crossing this dL perpendicular. All right, and you can define a quantity if you just look at the delta I by delta L perpendicular, and you take the limit as delta L perpendicular tends to 0, to define something similar to sigma there. Okay, the purpose of this K is to tell you how the current will vary from one point to another on the surface, just in the same way that sigma tells you how the charges vary from point to another on the surface. Okay, so it tells you information about that charge distribution. This tells you information about the current distributions, how the current varies from one lane to another. Okay, not the charge from one patch to another like here. Okay, so same story. If you have charges which are moving in 3D, then same story. Now you can divide. You're not gonna divide now. You don't have an area like a sheet that we had here. You have actually a volume. So the way you are gonna divide this whole volume is that you're gonna divide it into pipes. Okay, these are your lanes. They are pipes in 3D. So there are many pipes, each with some current dI, and after that, every pipe contains, just in the same way here, an amount of current dI, which is nothing but how much a charge is crossing a single pipe. Well, what does crossing a single pipe mean? It's just how much a charge is crossing this area. Okay, not a line, not crossing a line, or not crossing a point. It has to be crossing an area. So if you are to define a quantity which tells you or play the role of some kind of density which tells you how the current will vary from one pipe to another, you have to consider this ratio. So delta I by delta A perpendicular, so delta A perpendicular is the cross-sectional area of the pipe, and this is what we call or this is what's going to be the current density in this situation. So this is usually called volume current, and so this is volume current density. Forget to write that. And this K is called surface current density. I'm not gonna write it down. There's no place for it. Okay, but you get the idea. You can push this. You might be wondering why. Just a minute. You might be wondering here, for example, we you have surface charge density, so you have dq by dA. Volume charge density, so dq by d tau. So you have a dq here and a dq there, and for one-dimensional, for linear charge density, you have also dq. Okay, but when we came here, actually you have k, so di by dl perpendicular. For j, you have di by dA perpendicular. So why couldn't we have had something here also in the numerator, just similar to this? So you have a dq, a dq, a dq. You have here a di, but there's nothing there. Okay, and there's nothing there because this situation is not exactly similar to this situation. Here you can have a linear charge density which varies from one point to another, but here all that we have it's just one current, and that's it, and there's nothing you can do about it. Okay, so just one current per lane, and there's no meaning to talk about current density here, because we need to compare between currents at one lane and a nearby lane, but there are no nearby lanes here. While here you have these possibilities because you have different locations. Okay, here there's one current everywhere, and that's it. Okay, so there's no correspondence between these two cases. All right, so let's look at our first example for which we want to find the current density. So let's start by the definition. So this is limit delta I as delta L perpendicular, delta I divided by delta L perpendicular as delta L perpendicular tends to 0. And it's always good to keep in mind what these quantities mean geometrically. So basically you have some charge which is flowing over a two-dimensional surface, and you divide this whole surface into lanes, and every lane contains an amount of current delta I, and it has a width which is called dl perpendicular. And in every situation you calculate these currents and the current per lane and the width of the lane, divide them, and you take the limit, and this will give you k. Okay, so let's see how we can apply these concepts by starting this problem. So part A of this problem is to find the current density of the surface of this hemisphere. So this is what we have. It's supposed to be my hemisphere. It has some radius r, okay, and I have a current I, which just by symmetry is flowing symmetrically flows symmetrically down this sphere in all directions. Okay, so let me pick some general circle over which I know by symmetry that the current will be flowing in a symmetric way. So the current will be crossing this this circle exactly in a symmetric way. What do I mean by this? What I mean by this is if you divided this whole area into little lanes, so this is one lane and another lane and so on and another lane. This is why I'm saying that you should always keep in mind the meaning of delta I and what does it represent geometrically. So down every one of these lanes, so I divided the whole spherical surface or have a sphere into identical lanes, and every one of these lanes have some width, but as you see from the geometry, the width will vary from one point to another. But at least the lanes are identical, okay? So they look exactly identical. They vary in width in the same way as you go down the surface. So you expect just by symmetry that the amount of current in every lane, namely the delta I, if you divide it by delta L perpendicular, will be the same for every lane. So you have K over this first lane the same as K over the next lane and so on, okay? So you have the same K everywhere. So since you have the same K everywhere, you can calculate this by just dividing the total current, which we know that it's I, by the total distance over which this current is distributed, which is 2 pi d. So what's d? D is the radius of this of the radius of some general ring, okay? Because the same current will be distributed over larger distance, larger circumference as you go more and more down the surface. Okay, so let me use d with a different color to emphasize that this is the d of the circle, the straight circle. Okay, so we need to express this in spherical coordinates, and this d is not given in spherical coordinates. This is basically this distance, okay, from the surface all the way up to the z-axis. So how can we write this d? So the way you can write this d, and I'm gonna leave this for you to convince yourself that this is true, you can write this as r sine theta. So theta is the angle. So let me do it. So this is our ring here, and this is r. Okay, this is the distance we call d. We don't know what it is, and this is by definition the angle theta. Okay, so as you see, r sine theta is this d, right? So our k is nothing but I over 2 pi r sine theta, and you can add information about direction since the current is going, the flow of charges are going down over the surface, so this is theta hat. All right, so this is part A. Part B is exactly the same. The only difference is, again, the total current is distributed isotropically in all directions. So what you need to do is you need to do something similar, but now in the xy plane. So let's forget about the half sphere, and let's just draw a circle which sits in the xy plane, and over the circle the current will be distributed isotropically, like so. Okay, so I know that K, I can calculate it by dividing the total current over this total circumference. So what's this total circumference? So this is gonna be like 2 pi r. You can again do it in spherical coordinates, and that's it. And r is how far this this circle is from the center. What about the direction? So as you see, the direction is going gradually out. So I can write this as I over 2 pi r r hat, which will be true if you want to represent this in spherical coordinates, or if you want to do it in cylindrical coordinates, it is going to look like this: I over 2 pi s s hat. Okay, so maybe in this problem I could have written down, just express the surface current and so coordinates. All right, but this is the idea basically. Okay, so let's consider another example. So what we have here is a disk of radius r. It's painted with a charge density sigma, and the whole disk is rotating with angular velocity omega. So what we need to recall about angular velocities is the following, that omega by definition is d phi by dt, which is limit as delta t tends to 0 of delta phi by delta t. So this will be useful for our analysis. Okay, so let's have so we want to find the current density. So again, let's write down what it is. So by definition, it's limit delta I by delta L perpendicular as delta L perpendicular tends to 0. And again, it's useful to keep in mind what the delta I is, what the delta L perpendicular is, depending on the situation. So let's have a top view of this disk. So this disk is charged and the disk is rotating. So we expect that the direction of the current will be like circles, right? So it's natural to define or to divide the surface into rings like so. Okay. And in every ring, there is some amount of current di. So the ring in general has some radius. You can do this in cylindrical coordinates if you want. So every ring has an amount of current delta I. And once you determine what are the shapes of these lanes, so this is our lane for this example, you can tell immediately what should be, what is this delta L perpendicular. So delta L perpendicular is this distance in green. So delta L perpendicular, you can write immediately what it is, and this coordinate system, it's nothing but ds, delta S, okay? Okay, because the width of this ring along this direction is delta S. So with this in mind, we can start calculating our delta I. So again, remember, this is nothing but the current in any one of these lanes. Okay, and the lane has a radius r. So how to find the current within any of these lanes, how to find the current in general, it's the amount of charge divided by how long this charge take to cross certain point or certain distance or certain area as delta t tends to 0. So how we can write this delta q in terms of the information that we are given? What are we given? We are given sigma. So you can always write any amount of charge as the charge density times the area. So what's the area? Area is the area of little patch in 2 dimension. So in single coordinates, you can check this and justify that it has to be S delta phi. So sigma S delta phi. All right, so basically, let me do this in different colors. So this is basically the area that we're looking at. So this area in string coordinates is just s ds d phi. You can think of it as like a little rectangle, and you can justify that the dimensions of the rectangle is delta s and s delta phi. Okay, and then you divide this by delta t, and then you take the limit. And as we agreed, the limit as you let delta t tends to 0 of this quantity is nothing but omega. Okay, so now delta I within a specific lane of radius r is basically sigma s delta s. Okay, all right, then how to find k? Well, you take this delta I and divide it by delta L perpendicular, which is delta S. So let's write this again. So this is, so delta I, delta L perpendicular, so you substitute. So you have the limit, sigma is delta S divided by delta S, and you let delta S tends to 0. But as you see, these will cancel out, and you're left with just sigma times S. Okay, you want to add information about directions? Well, the current is going like so. So this must be along the phi hat, and you're done. Okay. Okay, so let's discuss another example. So in this example, we have a cylinder with the current density, volume current density now, rho, and again it's rotating. So it's rotating with angular velocity omega. So let's also keep in mind that omega is limit of delta phi as delta t when delta t tends to 0. So this is nothing but d phi by dt. Okay, so how we can do this? Well, since now your charge not only flowing over surface, but they are flowing in 3D, okay, because you have charges everywhere. Notice this row. So we need to look at the volume current density. So what's the definition of J? It's limit delta I is delta A perpendicular tends to 0. And again, it's very important to keep in mind or just a geometric picture of what these quantities mean. So J goes with some flow of charge in 3D. Okay, so you divide this whole region through which the charges are flowing into little pipes, like so. Okay, and within every pipe there's an amount of current delta I, and the cross-sectional area of this pipe is called delta A perpendicular. So depending on the situation, you calculate delta I. This is the numerator, and you calculate delta A perpendicular. This is the denominator. Divide them, take the limit, and this will give you J. Okay. So in this example, the charges are rotating around the z-axis, and we need to calculate delta A, and we need to calculate delta I. So let's do this step by step. So what's delta I? Again, this is how much current is within every pipe. So in this particular example, how do the pipes look like? Well, the charges are rotating, and they are rotating in 3D. So your pipe is actually circular pipes like this. Okay, and the charges are flowing in them and rotating in them. So this is a general pipe of some general radius S, okay, and it has some cross-sectional area which we can determine, which we'll determine in a few seconds. Okay, so let's calculate delta I first. So again, this is how much current is going through this little pipe. So it's a limit delta Q over delta T as delta T tends to 0. So you are given that the charge density is rho. So is there a way we can write delta Q in terms of rho? The answer is yes. So it's rho times the volume element, the little volume element in 3D in cylindrical coordinates. So you can check the formula sheet. It's S, delta S, delta phi, delta Z, and then you divide this by delta T, and then you take the limit as delta T tends to 0. And if you notice, you can already, this with the limit, you can identify as omega. Okay, so this becomes rho omega S delta Z. Okay, so this is our delta I. What about delta A perpendicular? So this is the area that charges at the flow intersect with perpendicularly. Okay, so what do you think this area is in cylindrical coordinates? So you need to look at the formula sheet and check the line element for this, and recall how we build areas out of line elements. So how to build this area? Well, this area is perpendicular to the direction of the flow. The direction of the flow is along phi hat, right? Because the charges are rotating. So what area element you can write down can be read from the line element by just multiplying the coefficients of S hat and of Z hat, right? So this will basically be so the direction of S hat, or the distance along the S hat direction, is delta S, and the distance along the Z hat direction is delta Z. So this is the area element perpendicular to phi hat, which is the direction of the flow of the charges. Okay, so what do you do next? Well, you divide delta I by delta A perpendicular. As you notice, you have here delta S, delta Z. Delta S, delta Z, they are gonna cancel out, and eventually your J will be only rho times omega times S. Okay, and you can add direction since the charges are rotating along the phi hat direction, so this is the direction of J. All right.